I'm going to go ahead and make just a couple remarks. We're probably still waiting for a couple students, depending on exactly sort of who's here today. Just quickly and brief, if you're going to resubmit homework 1, I gave everyone the option to resubmit answers for problems that they can get full credit on, and you can get sort of half of the available points. But that has to be due on Friday. I can't keep putting it off in fairness to everyone. I want to be able to get back the assignments to you guys with some answers, solutions, that is. And you've got other things I know ongoing for the class. I know that's extra busy, but I think it's a pretty fair opportunity. So bottom line, you've got a homework assignment due on Wednesday, I think. Mike Loescher is the TA for this assignment. He's going to be here at the end of the lecture to field questions. We tried to get your answers to questions over email. I apologize if that wasn't quick. I was at a conference until late on Saturday. So at any rate, keep the questions coming, and Mike will do his best to answer them. Again, he'll be here at the end of class to field some questions for a little while then. There's office hours today, there's office hours tomorrow, there's office hours tomorrow, and then the assignment's going to be due on Wednesday. If there's a need to meet the TAs, just reach out to them. They're nice guys, and they'll carve out time, but only if you seek them out. Yeah, hours.
So the homework's due on Wednesday at 12 p.m. Right?
I forget what's written on the assignment, but
Wouldn't be able to ask questions about the homework too. Right?
Yeah, so I'm flexible to change the time of the due date. And I don't know if that's what you were getting at, but I'm fine with that. So, I mean, presumably that would be a helpful thing?
Yes.
So, no. Make it earlier. Okay, so, I'm pretty flexible about that. But I think there's a limit too, right? If I set it to 12 p.m., that just means you guys are going to stay up, or 12 a.m., you guys are just going to stay up that late, right? So that's fine. There's always like enthusiastic nods. Okay, fine. So I don't actually really care because I'm not going to start grading it in the middle of the night. But why don't we just say it's due at midnight then?
Thank you.
Yeah, sure. And then if you look at my exponential penalty, it's pretty forgiving, right? So if you're really, really pressed for time and you don't hand it in for a day, you only miss like a half a point or something. So it's not too much T2K. So just those couple comments. Your lab assignments are due on Friday. You know, I'll be truthful. The labs aren't that bad. Like, there's a little bit of analysis to do. I don't grade the labs really hard. It's mostly about you guys getting some hands-on experience with the scanners and with working with some data. So those are certainly graded more easily than the homework assignments themselves. But that's really about all I can say about it. But the reports are short, and they're short because I don't want you to spend a ton of time on it. So keep that in mind when you're trying to balance your time amongst this and several other things. So I think that sort of rounds out my comments about sort of homeworks and the lab. Any questions from you guys? Okay, so Mike will be here at the end, and he can say, I actually am going to have to go relatively quickly at the end of lecture. Today and for the next 2 lectures, we've got a guest speaker. This is Dr. Kyung Sung. He runs another MRI research group and MRI research labs here at UCLA, Department of Bioengineering and Radiology, and probably some other things as well. He's given these lectures a couple for many years, and he's got it really dialed in. So with that, I'll go ahead and let Kyung start.
All right, thank you. So my name is Kyung Sung. So today and Wednesday, I'll be actually covering more the signal localization. Part 1 is actually more the excitation perspective, and later we'll be talking about how do we design the readout and the frequency encoding and phase encoding gradients. And so, as I said, I'll be mostly talking about the excitation pulse or RF pulse. And in the excitation pulse, there are 2 types of pulses, kind of non-selective and selective excitations. So we'll be talking about those 2 aspects. Particularly, we'll be looking at the Bloch equations and see how does the gradient and the RF waveform can play a role in the non-selective and selective excitation flow. And then I'll be covering the small tube approximation, particularly the way that you understand the non-selective and selective excitation is try to solve the Bloch equation, and then the Bloch equation. To solve the Bloch equation is simple. So basically, you have to do some approximation to solve it, and then we're going to drive how to do that somewhat mathematically. So mostly, we'll be actually talking about the Bloch equation. kind of mathematical perspective as well as a kind of graphical perspective too. So you guys are familiar with Bloch equation, right? What is it? Can anyone tell me? Uh-oh.
Describes the function of the net magnetization.
Right. So based on like gradient and RF pulse and something else, anything kind of when you have the magnetic field, the Bloch equation kind of expresses how the magnetization changes over time, right? Okay. So again, this is kind of the definition or mathematical definition of RF pulse. You're gonna have the envelope function, which kind of looks very similar to sync. And you have a resonant frequency governed by the omega RF and the theta. Theta is just a constant phase, and omega RF is basically the resonant frequency for that, or the Courier frequency. And as you said, so as I said, the RF pulse is kind of including the omega RF, which is the Courier frequency, and the envelope function, which is B1 E of t. So in this case, you have a Courier frequency, which is kind of small oscillation, and a big kind of sync type pulse is going to be your envelope function. Any questions? The reason that I want to say is actually basically this is the definition of RF. Whenever I say B1 of t, that basically includes this. This theta terminology, theta term is actually the constant base. We're assuming theta to be 0 for the rest of the discussion. And later, maybe if you look at the adiabatic pulse or something else, this theta is important, but at least right now, we're going to assume theta to be 0. Any questions? Okay. So anytime, whenever you have any questions, just feel free to interrupt and ask anything. So this is kind of the typical way to look at the magnetization is flip whenever you apply this RF pulse. And we're going to actually take a look at very carefully how the Bloch equation explains this mechanism, like this graphical mechanism. Okay, so again, whenever you try to understand the excitation, I think you have to look at the Bloch equation. Bloch equation is, it's just a kind of first order differential equation. You need to solve it, and to do that, you have a B field, which is B0, which is the main magnetic field along the K direction, which is gamma times omega, which is your main resonance frequency. And also you have B1 of t. B1 of t is again, as defined as previous slide, you have envelope function, you have the carrier frequency, and then your B field is combination of your static field as well as your B1 field. So B0 plus B1. And then B0 is along K, and the B1 is along XY direction. So the direction only is different. So as I said, the B1 field is actually more related to the I and J, which is the transverse plane. And the K is more the kind of Z direction, the through plane. Okay? So the main task is, again, we know what is B field, which is B0 plus B1, which is this component. And we know the gamma. And we try to understand how the magnetization change over time by solving this Bloch equation. That's it. But, again, this Bloch equation is not easy to solve it, so it needs more kind of approximation later to have the analytical solution. So to do that, we need to actually kind of change the frame from left frame to rotating frame. So this is the left one is actually called a lab frame or laboratory frame, which is kind of the typical way to understand the magnetization. It has, again, the tipping as well as the rotation. If you get rid of the rotation portion and then only can take the tipping portion out, then it's called rotating frame. So that you can actually understand the tipping mechanism much better, or visualization is much better to understand the tipping. Because previously, as I said, this one includes the rotation as well as tipping, and the rotation is simply a rotation around about Z direction. So you can actually get rid of that rotation out and then the tipping is actually much easier to understand. So this frame is called rotating frame. I think previous lecture covered the difference between the lab and rotating frame, right? So again, always you have to take a look at a more mathematical point of view. So this is a mathematical point of view. I, J, K is a lab frame coordinate, and I prime, J prime, K prime is a rotating frame. The way it goes back and forth is basically including this rotation matrix about Z direction, and the rate is omega RF, which is a carrier frequency. So having or including this rotation about Z matrix or rotation matrix about Z can go back and forth between the lab and rotating frame. And rotation matrix is simply just cosine sine term. And again, the rate of that rotation is governed by omega RF or carrier frequency. Any questions? Okay. So this is again rotating frame. So the magnetization should be redefined as rotating frame, which is M rod, and B field should be also redefined as a rotating frame. And the way to go from lab to rotating frame is to add the rotation matrix. And the rate of that rotation matrix is governed by omega RF. It's just simple. You just multiply by this rotation matrix, which is defined by here. And then you have the rotation, magnetization, and then B field in a rotating frame. Then the whole reason that we do that is we need to redefine the Bragg equation in a rotating frame. So the prior or previous Bragg equation is based on the lab frame. So we are actually going from the lab frame to rotating frame. And the only changes is actually your rotation, the magnetization in the rotating frame and the B field in a rotating frame. Okay? And then so this B rotation is easy. We'll actually cover how do we look at the B effective. The key portion to understand the excitation is to understand the B effective field. If you understand how to look at the B effective, then you will have much better idea on graphically how does the excitation work. Okay, so the Bragg equation in the rotating frame is written by this, and as I said, the B effective will be defined as B rotation plus R omega rotate divided by RF, the gamma. This is basically some fictitious field. It's just kind of subtracting the omega RF. So you can think about it in terms of kind of B field. You're getting rid of the omega portion out because you're multiplying by the rotation matrix at the rate of the omega RF, right? So if you just get rid of the omega RF along Z, that's basically the B effective. Omega RF is given because whenever you have the RF pulse, you know what is carrier frequency. So this is somewhat fixed value, and then just adding up whatever the B field that you're applying to, then you're going to have a B effective. I'll be actually covering more the graphical view for that, so don't worry too much if you kind of lost what's going on here. So, as I said, the B rotation is going from B lab to B rod. The only thing is actually just getting rid of this omega T portion. So everything is just B1 and B0. So if you're assuming the B1 of T is a real value, then it's going to be just envelope function. And then you're not going to have this. You only have envelope function along one direction, one axis. In this case, X. And then B0 minus omega RF divided by gamma. So if it's on resonance, if it's at on resonance, then this will be the same. Because omega RF is tuned to your resonant frequency, and then this will be canceled out. If there's any off resonance, there will be some residual term here. Okay? So at on resonance, it's going to be canceled out. Everything will be left over as a real valued envelope function. This is your envelope function of your RF. So whenever you have envelope function, B effective will be envelope function along X direction if it's at on resonance. Okay, so I'll be actually covering a little bit of the examples for that because I cover a lot of mathematics. So let's go to the doc and then I'll be talking about this. So example 1, let's assume that you have a B1 field which is constant during a certain period of time. So meaning you have during 0 to tau, you have a constant B1 field, which is B1. It's a real value. Can you see this well? Okay. And mathematically, B1 of t is equal to B1 during 0 to tau, right? And then the B effective will be, as I said before, B1 of t 0 and B0 minus omega RF gamma, right? And if it's at on resonance, then this will be canceled out, right? And then the B1 of t is only B1 during the time. So this will become B effective will be just B1 0 0 at 0 tau, right? So let's look at like graphically what's happening. So graphically, you have z direction, x and y, right? B effective will be B1 during that time. So B effective will be just purely this. And then you have magnetization, right? So you have magnetization like this. So this is magnetization and not. This is your B effective, right? And then using your left-handed, rotation rule, during the time that it has a B effective on, you're going to have rotation. Your magnetization will have rotation. So this will be rotated. Like this. And the amount of rotation is called flip angle or tip angle. So your tip angle theta will be gamma times, in this case, you have constant B1. So the B1 during tau, so tau, that's going to be your tip angle. Because it's going to be rotated, the magnetization will be rotated only during the tau, and the amount of the strength is governed by B1, which is the amplitude of that. So the tip angle theta will be calculated by gamma times B1 times tau. That's your amount of that.
Just to be clear too, we've been calling that alpha.
Okay, sorry.
It's okay. It's a little hard. Like, don't change your notes because it
Okay.
might be confusing,
Okay.
But for you guys, you can remember that.
Yeah. So either you can use alpha or theta. It's here we're defining as a tip angle or a flip angle. So flip angle or tip angle is defined as like this: 0 to tau gamma times B1 of t prime, t prime, And in this case, during the 0 to tau, which is the pulse duration, it's a constant value of B1. So that's why I'm getting gamma B1 tau. Okay? Did everyone get it? Okay. Let me just change the... Okay. So to give a number, so I will give some numbers. If you want to achieve 90 degree, right? So what if you want to have theta to be 90 degree? That's pi over 2. And assuming your pulse duration is only 1 millisecond, then what would be your B1 amplitude, right? Required to achieve 90 degree. So let's go back like a backward. So again, as I said, theta is gamma times V1 times tau. And this you want to have pi over 2. This you're having 1 millisecond, right? So in this case, if you do a math, and you know the gamma, so if you do the math, B1 should be around 0.06 Gauss or 6 microtesla. So if you put 0.06 Gauss over 1 millisecond, then your magnetization will be tipped over 90 degrees. So another question is actually, so this is kind of like you apply the B1 field at certain number, and then you're going to achieve certain flip angle value. What if some sort of system doesn't allow you to have a constant B1 across all the objects? So meaning, what if you have different B1 amplitude in different locations? So meaning you are assuming you have certain value, but then for some reason, maybe the system doesn't allow to do that, or the body doesn't allow to do that. You're having a different B1 amplitude in different locations. Then what's happening? So again, if you're using the 0.06 Gauss or 6 microtesla, your magnetization will have 90 degree excitation. With a certain B effective. Right? But if you have some reduction, then, like for example, if you have a 50% reduction in amplitude, then what happens is you only have half of the amplitude as B effective. Then what happens is only you're going to have 50% reduction in flip angle. The reason that I'm saying here is actually, so this B1, it's called B1 inhomogeneity. So it's a well-known problem for high field MRI. So whenever you have a higher field strength, typically because of the tissue dielectric effects, you're not going to achieve the same B1 field across the body. Typically, the reduction or overachieving of the B1 field is commonly happening. And then what's happening is actually eventually it's going to have different flip angles. So the B1 inhomogeneity is really common for high field imaging, particularly for 3T or higher field. And then because of that, you're going to have different flip angles, and then it creates a lot of problem for diagnostic imaging. So it's a huge kind of area of research. The first question is actually, how do we measure a different B1 field in a different location? So so-called B1 mapping is a big issue. And then once you measure the B1, how do we compensate it? Because in this case, at certain locations, you're going to have 45 degrees. In certain locations, you're going to have 90 degrees. How do we do that? Because you already achieved the flip angle, and then your image or the contrast or image intensity will be different. Although you know that information, it's also very challenging to compensate that. So it's very active research area. Still, if you go to ISMRN, there will be a B1 mapping session, which is the MR conference, and people still talk about how to measure it, how to compensate it, and so on and so on. So it's one of the kind of the technical challenges at the moment. So I just want to bring that up as a kind of as one of the interesting topics. So let's go back to this slide. Okay. So far we actually covered the kind of looking at the B effective, and the definition of B effective is always your envelope function, which is a real value, and then B0 minus omega RF divided by gamma. So at on resonance, basically this will be canceled out. If it's not on resonance, then it's not going to be canceled out. So that's kind of how you look at as a non-selective excitation. So you apply the B1 field, and then there's a magnetization. And if you solve the Black equation, you can see the magnetization is kind of rotated. It doesn't matter at Z equals 0 centimeter or 10 centimeter, 5 centimeter or something. It's non-selective. Everything is tipped down as long as you have a B effective field there. So how do we design the selective pulse then? Selective means you specifically say, within this 1 centimeter area, we want to tip it, and everything else won't be tipped. So how do we design it, right? So that's the next question. And then the important role is based on the gradient, because the gradient will be giving you a different magnetic field at different location. And whenever you have a different magnetic field, it's going to actually make you be very selective excitation by designing an RF pulse. So in this case, I'm kind of showing if you apply the X gradient, then it's gonna select the YZ plane. If you apply the Y gradient, and it's gonna select the sum slice in the XZ plane. If you have a Z gradient, which is very common, then you will be selecting an XY plane. So depending on what gradient you're using, you can actually selectively excite this certain area. So it's called selective excitation. Any questions? I think you saw this diagram a lot, right? So we're going to actually take a look at why this is important and how it's going to work in terms of like mathematically and graphically by solving the Black equation. So gradients. Gradient produces a spatial distribution of frequency, and then it's going to be defined as B0 plus gradient times location. So when you apply the Z gradient, your B field along Z will be consisting of B0 plus gradient amplitude times location. So meaning, if you look at a different location, your B field will be different for different locations, right? I mean, here we're actually getting rid of the b part, but b0 plus zz times location is basically linear component plus b0. So if you have a bigger gradient amplitude, if you're using a higher gradient amplitude, then this slope will be higher, and then you have more kind of differences in the frequency. If you have a smaller gradient, then this slope will be lower, and then your range of the frequency will be narrower. Okay? And then same thing, if you look at the omega component, just multiplying by the gamma, then it's the same thing. It's omega 0 plus this gradient times, gradient and having a different values at different locations. So there is a direct correspondence between the frequency and spatial position, particularly at different spatial location in Z will create different or will have different frequencies. And that different frequencies will be governed by gradients. Here, the gradient amplitude along Z. Okay? Why do we talk this? Because this is important to understand the B effective. Because when you apply the gradient, B effective will be also somewhat affected, and this will be exactly, you need to put it in your Bloch equation. Okay, so same thing as I said before, we have to solve the Bloch equation in the rotating frame. For the non-selective cases, you only have real valued envelope function, and then B0 minus omega RF divided by gamma. When you apply the gradient along Z in this situation, things will be B0 plus ZZ times Z, and then because it's a rotating frame, you have to subtract the omega RF divided by gamma. So kind of like when you apply the gradients, without gradient, it's just B0, right? And then you add this gradient, and then the B field along the Z will be consisting of B0 plus ZZ times Z. So now it becomes like that. Okay? So again, the B effective field will be looking like this, and at on resonance, basically this will be cancelled out. B0 minus omega RF divided by gamma will be cancelled out. The only thing left is gradient. Okay? So the way to look at the B effective will be different now because of the gradient portion. It's no longer B1, 0, 0. It's going to be B1, 0, and the gradient portion at on resonance. If it's off resonance, things are different, but to make it simple, we're just looking at the on resonance status, and things is only governed by this gradient amplitude. And again, if you look at this Bloch equation as more matrix form, this will be like this. This is omega as a function of Z, which is this component. So this will be omega Z, and this will be omega T. So there are two components in your matrix form for the Bloch equation. There will be omega as a function of location. There will be omega as a function of time. Because your envelope function of B1 is changing over time, and your gradient or the frequency will be changing over locations. So that's why two expressions again, omega Z and omega 1. And again, it's just exact same thing. This is exactly the same as this, but just putting in a matrix formation, and we're solving this in the magnetization, how the magnetization changes over time. Okay, so omega Z is basically gamma ZZZ, omega 1 is gamma times B1. Okay? Okay, so another example. So I'll be putting an example 2 in this case. So let's say there's no RF pulses, only gradients existing. So let's just assume no RF pulse, only gradient. By the way, the notes will be available on the web, so don't worry too much on my bad writing. So again, B field or BZ along Z will be B0 plus ZZ times Z along K, right? And then B effective, and right. So this can be B field because B1 field because there's no RF pulse, right? And then B effective will be same thing, B0 minus omega RF divided by gamma plus gradient along Z times different position along K. So on resonance, basically this will be cancelled out. You only have a gradient or different frequencies at different position. So how do we look at it? This is basically, you have a Z, X, Y, and then the B effective will be different at different location, and then it's going to be like this. Depending on location. So what I want to say is at Z equals 0, everything is 0, so things will be here. If Z is positive value, then things will be up here. If Z is negative value, things will be over here. So depending on different location, B effective will be different. So those are kind of different B effectives at different location. Okay? Now, why don't we kind of combine everything together? So we actually cover the RF constant during that time. We actually cover no RF, just a constant gradient over that time. So why don't we kind of combine together? So what if we assume there's a B1 during the time, constant. There's a gradient during the time, constant. So the next example, sorry. Next example will be so 0 to tau, B1. So this is the RF pulse. And then time 0 to tau, ZZ, and gradient only. Okay? Okay? Then, again, we always have to look at what is a B effective. B effective will be having two components along K and along I. So B effective will be B1 along I plus same thing over here. Okay. And as I said, at on resonance, this will be cancelled out. Okay, so how do we look at it? So let's look at the Z equals positive value. So if Z equals z1, which is positive value. So at z equals z1, right? And then let's look at what's the b effective. So there will be a b1 component along x direction, and there will be gradient times position component, which is along z direction. And then it's going to be a vector sum. So it's going to be something like this. X, Y, Z, and this is B effect. Okay. What if location is 0, so Z equals 0? Then X, Y, Z, there will be only a component along X, which is B1 equals B effective. What if location is negative value? So when Z equals negative Z1, it's the same thing. Z, there will be B1 components and negative components. So this is B1 and ZG times Z, then there will be a vector sum. Okay? So what do we see here? So I just want to say B effective will be different at different locations, right? So just assuming if this location is really, really large, so meaning if this is huge, right? I mean, this won't be changing at different locations. So the V1 is always constant. But if the location is much higher, so that this component is much bigger than this, it's almost perpendicular to the V location, right? That means there's no excitation, because your B effective field is close to M naught, there's no rotation. Same thing. So at Z equals 0, it's the same thing. If there's a M naught component, you're going to have rotation because of the B effective field. It's the same thing as non-selective situation. So if the location is 0, it's exactly the same as non-selective excitation. You're going to have excitation based on your amplitude and time. If the location is far off, then this B effective is actually very close to Z, and there's no rotation. Same thing over here. If the location is far off, the vector sum is very close to the negative Z axis, there's no rotation. So what that means is actually, depending on the location, this gradient times Z location will be somewhat changing. And if it's dominant compared to B1 field or B1 value, then there's no excitation. If it's small, so that it's close to the original B1, then still you're going to have some excitation. What that means is actually it's basically selective excitation, depending on location. So how do we do it? Depending on how you put the gradient, right? Depending on how you put the gradient, how you put the amplitude, things will be different at different location. And then it's going to govern the flip angle and the selectiveness of your slice profile. Any questions? Too much stuff, or is it okay? Is it so far okay? Okay. So, no bad. So this is called slide selection. So as I said, depending on your gradient amplitude, you're going to have different selection, and this will be governed by the amplitude of gradient and location. So let's look at it. So the way to look at excite a certain slice is basically you're going to have changes on the frequency. So there will be a certain range of frequency existing depending on your RF pulse. So your RF pulse will have a certain kind of frequency that can be selective. And then when you apply the gradient, depending on the gradient, you're going to have a certain spatial location to be selective. Okay, the way we look at is when you have a different B1, the example was actually a very simple kind of B1 field. You have very constant B1, there's no oscillation. So assuming if your RF pulse has a certain selective property in terms of bandwidth. So if you think about your RF pulse as a specific bandwidth, meaning you only select certain kind of frequency area, when you use a different gradient, that translates to a certain location of the selectivity. What that means is actually, even though you're using the same RF pulse, depending on the gradient amplitude, your side thickness or delta Z will be different. Or with the same delta Z or the side selectiveness, with the different gradient, you have to change the bandwidth of your RF. Any questions?
So does that essentially mean that you have better spatial resolution if you have a smaller gradient relative to the RF pulse?
Here the resolution is a little bit different. Maybe like slide thickness is actually better terminology here.
Okay.
So you're asking like a finer.
Yeah. So like, isn't it that if you have like a thicker slice, you're getting too much information? I guess, like about you're not really selective about your slice.
Right. So the point here is either you want to have a thicker slice or thinner slice, depending on your questions. You can design RF pulse by basically having a different bandwidth of your RF and different gradient. So for example, if you want to have like a very thin slice, right? That means you want to have this to be really small. What that means is actually maybe you need to have a higher gradient or you have to have a very thin or the small bandwidth RF pulse. It has to be a combination of both, because in some situations people want to reduce the bandwidth, but the RF or the MR physics doesn't allow you to go from somewhere beyond certain limitation. In that case, you have to change the gradient, or the gradient has also limitation because the system has the high gradient power, and then you have a limited gradient power. So depending on the situation, you can actually change either gradient and or the RF bandwidth. The key point here is actually you can change your side thickness based on your design criteria.
Could you talk about how you change the slice location?
Oh, slice location. So how do we change the slice location? Can anyone tell me maybe?
You change your center frequency.
Yeah, exactly. Yeah. So exactly right. So if you change the center frequency, that means your center point is different, and then you're gonna have the bandwidth, and then you're gonna excite different location. So for example, like if you want to excite the maybe did you cover the fat suppression or fat? Yeah, so if you want to excite the fat only, fat has a different resonance frequency, so you can actually add a instead of focusing your center frequency to be the water resonant peak, you can actually set up as a fat, and then you only excite the fat rather than the water proton density. So that's possible, or you can actually, yeah. So you can use it different locations or different components to excite it. Okay, so this is kind of somewhat related to the kind of how to set the parameters. So basically, you have to choose the delta omega, which is your bandwidth of your RF, and then based on your gradient will be determining this slope, and then you have the delta Z. So in a reverse way, if you want to have 1 centimeter kind of excitation, or for example, if you really want to have thin slice, so like you want to have 1 millimeter excitation, then you set this to be 1 millimeter, right? Either you choose a gradient that kind of translates what should be the bandwidth, or based on a bandwidth and a design criteria, you can actually set the gradient amplitude. Normally, what's happening is actually later because it's really hard to change the RF bandwidth. So in practice, what's happening is actually this is more given, and then you want to change the different side thickness. By doing that, you have to change your gradient amplitude. Yeah, so this is kind of, you want to have so this is the slice profile. This is your RF bandwidth, and you have certain bandwidth as a rectangular. So if you have a certain frequency selection, it's going to be translated onto the slide thickness. And what's ideal situation is actually you want to have as rectangular, you want to have rectangular as much as possible, because you don't want to have a signal outside the slice. So you want to have the rectangular profile, but then you want to have the rectangular profile. That's your ideal situation. And then you have to design the RF pulse that fits this design criteria. So in the kind of RF pulse design side, so a lot of kind of research is also going on designing the RF pulse. So designing RF pulse consists of many different aspects, like designing the certain bandwidth, or designing the shape that's close to the rectangular, or if you have certain difference, if you have a different motivation to make the slice profile to be different, then you have to design RF pulse that fit it to this shape. But in most cases, you want to actually select certain location and then the other to be 0. Does it make sense?
What is the delta omega?
So delta omega is basically your bandwidth. Whenever you have the RF pulse design, you have to have a RF bandwidth. This is your RF bandwidth.
So is this trying to make sure there is a location?
No, this is more kind of like how thick your slice should be.
If it's how thick it should be like oh no, I don't mean the X delta omega. I mean the center.
Oh, this one. Yeah, this is the center frequency, right? So that's a location, right? Sorry. That's a location, right? So so selective excitation it's a huge area for research too. A lot of cases, changing the shape of the pulse, that's going to be affecting the bandwidth of the excitation, and in many cases, right? In practice, what's happening is actually we are having some ideal situation. We want to have this happen. And then the question is actually, how do we design RF that fits this kind of requirement? Is it possible? And a small tube approximation will be telling you that this tube will have close to have a Fourier transform relationship. So this is one of the reasons that a lot of people kind of based on an electrical engineering background, particularly for signal processing background, kind of jumping into here and initially contributed a lot because this is what it means as filter design. Basically, you have certain criteria, and then using a Fourier transform, like this is basically bandpass filter design. You have certain frequency that you want to excite, and then you want to design certain things. So initially, kind of a lot of people from EE side, they actually contribute, like adapting their kind of filter design and bandpass filtering ideas onto here, and then contributing a lot. But the whole behind scene of that is these two will have Fourier transform relationship, and roughly we want to have a rectangular as ideal size profile, right? Then what's the Fourier transform of the rectangular shape? Sinc, right? So prototypically, people use some sort of sinc-based RF shape. Either sinc with a windowing function, or simply like a Gaussian function or something are very, very commonly used. And the reason or the logic behind is actually basically this is a Fourier transform relationship. The rect function, the Fourier transform of the rect function will be a sinc function, and some sort of variation of the sinc function will be adequate to achieve this rectangular shape. If you want to have different shape, like a triangular or something, you also still can design RF pulse that fit it to that, but sometimes it's not clear why you want to have rectangular because it's going to be projected signal. But depending on the situation, you want to have different shape. But in most cases, you want to have very rectangular shape. Any questions? Okay. So the next step is, this is after the small tip angle approximation. How do we go from, so like I'm actually going to cover how do we go or how do we see this relationship by doing an approximation. So again, it's called small tip approximation. Small tip approximation is basically, again, you're going to have a Planck equation, which is m over time, and an m here, and then there's omega of z and omega of t. So there will be a frequency dependency on locations and a frequency dependency on the time. And the way it works is actually basically mz, which is the longitudinal vectorization, is almost same as m naught, which is initial status. So after tipping it, everything is almost, in terms of kind of longitudinal component, it's almost the same. Meaning, if you think about, kind of like this is your vectorization, if you tip very small, which is small tip, then longitudinal component will be very similar. So this is what it meant. mz after tipping is equal to almost same as m naught, which is initial before tipping. And then once you assume that, you're going to solve the first order differential equation, and then this will be your final kind of derived equation for that, which is kind of, you can see as a Fourier transform. So I'll be covering how do we go from there to the Fourier transform relationship. Okay, so we're going to cover the small tip approximation. Okay, so first I'll be covering the full analytical solution, and I'll be saying it's too difficult. So for solution, we have to solve this Planck equation. right? So this will look at mx, my, and mz, and typically the transverse component mx, my, and the mz are kind of behaving very differently. So we're going to actually use a phasor representation. Meaning you're going to define as mr as mx plus, this is a complex value, my. So we're going to use a complex notation to represent the x and y component. Then this whole Bloch equation can be separated as mr and mz. So there will be dmr dt plus I omega z mr plus omega 1 t times n. So I'm just kind of rewriting this matrix formation by using this phasor representation. Okay, so what we need to do is to solve two first order differential equations. Pretty simple, right? No. So this is somewhat looks simple, but this is not simple at all because you have two first order differential equations. Those are interconnected. So very, very hard to solve it. So that's why we need to have a approximation. So the small tip approximation, what it does is basically as I said, mz is equal to m naught, and tip angle is really small. In that case, sine theta is equal to theta, and cosine theta is equal to 1. So the key component is this. So once you assume mz is close to m naught or equals to m naught, what that means is actually it doesn't have any time behavior. So this differential equation is 0 because you don't have any changes over time. So what that means is this is constant. So any derivative of constant is 0, right? So if you rewrite it, you only have one first order differential equation, which is kind of possible to solve it. So all you need to do is basically solving this equation. Okay? And I'll be giving you some example on simple solution for first order differential equations. Okay, so when you solve the first order So there are a lot of kind of pre-defined solutions available. I'll just give you a simple ways to solve it. You can actually define as dy dx plus px times y is equal to qx. Then the solution of y is like this. Where ux is basically exponential. So it's very simple. Whenever you have a first order differential equations, and if you put it as this formation, the solution is like this. So let's go back to our initial problem. So initial problem that we try to solve is this, right? dmr dt and then if you kind of relocate it, will be plus I omega z mr is equal to I omega 1 t and that. So what it meant is actually basically mr is y, right? And t is x. And this portion will be px. And this whole portion will be qx. Right? Then, using this predetermined solution, I mean, you guys can actually do the work later, but basically, kind of like if you put ux like this, and then just put ux like qx into there, you're gonna have this solution. It's the same thing, just rewriting it and cleaning up a little bit of math. Okay, so what is omega t again? It's gamma times b1 of t, right? So this is what? The envelope function of your RF, correct? What is omega z? It's gamma zz times z, right? If there's only gradient along z. So this is basically kind of function of z governed by gradient, and this is a function of time governed by b1 envelope function, right? So once you have this and that, then we can see what will be your magnetization after tip, right? Or during the time. So this will be a kind of evolution of time and location. So this will be a function of z and time, because there's a time and z. Okay? So, let's assume RF pulse is symmetric. So what it means is actually basically you assume So you assume this to be symmetric. Then instead of starting the time on here, why don't we kind of shifting the time over half duration of the pulse duration? So what it does is actually basically we wanna redefine tau prime as tau minus tau p over 2. So this is kind of like mathematical kind of reformulation to make this look more Fourier transform. The way it does is actually we just assume that RF pulse is symmetric, and then shifting this RF pulse to be centered around 0. Because time, there's no negative time, right? So always the RF pulse starts with 0 time, but for mathematical perspective, we want to have more symmetric properties. So we just want to redefine tau prime by shifting the 0 axis to be centered around the RF pulse. That's it. And so new definition, just put it over here in tau. Then you're gonna have this. Then you can rewrite the MR as yeah. This is basically you just put the tau and tau prime plus tau p over 2, and then if you put it over here, and then things will go out, and then just kind of cleaning up, you're going to have this. Oh, sorry. This will be a function of the. Sorry. Okay. So just reformulation of the mathematical expression. Okay. And because we are assuming the RF pulse is actually 0 outside the pulse duration, we can actually put these things to be negative infinity to infinity. Okay? So because everything is 0, instead of integrating over this period, we can integrate over entire period. Still, the number will be the same, right? So assuming you can put negative infinity, infinity, and you have some function, and then you have exponential, nice exponential term. What is this? This is basically Fourier transform, right? So Fourier transform of what? This function. This is what? This is RF pulse shifted by half pulse duration. Correct? So this is nothing but just shifted by half duration. Once you put it there, and you can take a look at here too. This is a constant, which is initial magnetization. This is just a phase term. So if you purely look at the magnitude of that MR, which is the magnetization on the transverse component, this is phase, this is constant, this is also I, phase, nothing. The only thing that matters is Fourier transform of what? Omega 1, or gamma times B1, shifted by half duration of pulse duration. Right? And next, you may actually bother by this component. This will be canceled by the refocusing pulse. So you saw in the previous lectures, there is always, RF pulse, gradient, and the refocusing pulse, right? The main reason that you have the refocusing pulse is actually to get rid of this component. And this is what? Tp over 2, which is exactly the same half of the area of the gradient during the RF pulse. So if you have the refocusing pulse, this will be canceled out. Everything will be m naught times Fourier transform of your B1. Okay? So in other words, you can actually write it as MR is equal to I times M naught and Fourier transform 1D omega 1 . The reason that we have to put f as this is because omega z is what? Defined by gamma times zz times z, right? And always, if you're going to put as Fourier transform, there should be a 2 pi component. So you multiply by 2 pi, divide by 2 pi. That goes into here. So gamma over 2 pi times zz times z is the definition of your frequency, because this is a function of z, and this is a frequency definition. So it just mathematically, I just put it there. It's a gamma over 2 pi times zz times z. The reason that 2 pi is actually, we want to have 2 pi over here, and then we have to divide by 2 pi. Okay? Again, the cleaner version will be available on the web, so don't worry about too much if you don't get the small details. The whole point here is actually, again, we started from what? The Blage equation, solving the Blage equation, but then we need to solve 2 first-order differential equations, which are very hard. So we approximate to be m naught, or mz is almost similar to m naught, and the tip angle is really small, so that the sine theta is almost equal to theta, cosine theta is equal to 1, right? By assuming that, you only need to solve what? 1 first-order differential equation, which is this guy, or this guy. And then by solving the first-order differential equation, you have this, and then rewriting it, just kind of doing a mathematical massage, you have the expression on Fourier transform. So the beauty of that is this is analytical solution, right? So whenever you have a certain V1 over time and you have a gradient, you can analytically find what's going to be your MR, or the transverse magnetization over time and over space, because this is, again, a function of time and location. Okay?
Professor?
Sure.
Why is there a minus?
Yeah, the minus, it doesn't really matter. I think it's more kind of like you want to make the inverse or forward transformation. Everything is kind of symmetrical, so the minus doesn't matter. It's just kind of like making sure that this should be a positive or negative depending on a forward Fourier transform or negative backward transformation. So the sign doesn't really matter here. Any other questions? I know I kind of covered a lot of math stuff today, but at least kind of the notes will be available, so you can go over the details, and then you will get a better idea on what I'm talking. But the again, whole idea behind is once you have a very powerful tool, which is a Fourier transform, then you don't have to go back to the Blage equation and try to solve the first order differential equation. Now everything is a Fourier transform. So whenever you understand the Fourier transform concept, like rect is a sink, something and in frequency domain and different things, you can directly map it over here and then get an idea on when you have a Fourier transform, what's going to when you have RF poles, what's going to happen in the spatial domain or size domain. Or vice versa. Like if you have a certain design criteria, like you want to make size profile to be certain shape, you can design the RF pulse by applying an inverse Fourier transform, right? So there's a lot of possibilities is there once you put the kind of Fourier transform framework here. Okay? Any other questions? Sure.
Do we still need to amend the phase term, the first phase term?
No, so this will be taken care of by the refocusing pulse.
But I mean, if you solve this Fourier transform, you will get this phase term out. So
Right.
in the final solution, you will.
Yeah, so the easy way is just take the magnitude out because the magnitude is more important. Because again, there is component I which change the axis. There will be a component here, but other than that, other things will not create any kind of phase issues. So easy way is either you get rid of this kind of analytically out, assuming you have refocusing pulse, or you can just take the magnitude portion. So either way should work. So when you think about it, if you assume you have refocusing pulse, then you can actually get rid of it, and then everything else would be R times M naught times Fourier transform. Any other questions? Okay.
So, you covered your slides for today, right?
No.
No, you're going back?
Yeah.
Okay, I was just gonna say, could you remind them about the assumption of all this, like we
Sure.
started with?
Yeah, so assumption again is this guy, right? So assumption again is these three. After tipping, you're assuming that initial magnetization is same as the longitudinal magnetization. If the tip is really small, then you can assume sine theta as theta and cosine theta to be 1. This is very prototypical assumption when theta is really, or angle is really small. So this is why so-called tip angle or small tip angle approximation. I think the reason that Dan brought up this kind of assumption is actually, you may actually think, wow, this is really a very, rigorous, or I don't know, for some reason, this is like really tight approximation, right? Meaning you're assuming a lot. You're only looking at like 1 degree or 2 degree flip angle rather than like 10, 15 degree flip angle. But surprisingly, it works really good until 90 degrees.
That's not obvious.
That's not obvious. But even though it starts with like a small tip approximation, up to 90 degree, it actually works magically well. But then over 90 degree, it's not going to work well. So last one is actually, I have some example on small tip approximation. So let me just give the example to give some numbers. Okay. Okay, this is example. Let's just assume your B1 is rect function again. So B1 of t is B1 times rect function, which is symmetrical, and the pulse duration is tau. So graphically, you can think of as this tau t 0 B1. It's exactly the same as when you assume in a previous example, but kind of we want to look at it as mathematical point of view, particularly using a small tip approximation. So let's use a previous derivation like this, right? We're going to actually use this equation. So here MR is equal to I M naught Okay, so this is again the final product of this small tip approximation. All we need to do is just plug this omega 1 as defined as this onto here, right? So what is omega 1 of right? So if you put it over here, and if t is equals t plus tau over 2 will be cancelled, and then this will be t over tau, right? And these two are constant, you only have rect function. So right, just putting this onto here to see whether what's going on over here. What is the Fourier transform of rect? It's a sinc, right? And when you divide by tau, what's happening? Yeah, so rect t is sinc f. Rect t over tau is what? When you divide by something, always you have to think about it. The Fourier transform is always, when you stretch it, it's squeezing. So when you divide it, you have to multiply it. So if you divide by tau, that means tau times tau f, right? So the sinc will be tau times sinc f tau, okay? It's easy thing. So that's gamma times b1. Those are constant, and then tau sinc tau f, and then f is what? Gamma 2 pi z, right? So if you put everything there, everything here, and everything here, then let's see what happened. Okay, I think someone asked, like, there's negative sign, right? But sinc is symmetric, so it doesn't matter whether there's negative or positive. So just get rid of the negative sign. But when you put everything onto here, it's like this, right? Okay. As I said, this will be canceled out because of the refocusing pulse that we're going to use. This is constant. This is constant gamma. This is constant v1. This is constant tau, right? The only thing will change over space will be what? This, right? So we can see what's happening over space domain or spatial domains. So this is along z. Again, so this will be canceled out by the refocusing gradient. And then, again, it's going to be sinc by what? N naught gamma b1 tau. That's going to be the peak amplitude, right? So the peak amplitude will be n naught gamma b1 tau. And then, this is sinc, right? So there will be a sinc. Right? So there's an infinite sinc. So what it means is actually there will be a selection in Z, but then there is some residual stuff over there too. And this delta Z is equal to 1 over this component, right? Tau. right? So the width of the main lobe is basically 1 over constant times, whatever z. So the delta z will be 1 over this term. Okay? So what it says is what? Basically, if you apply the B1 as a rect function over tau and apply the gradient over tau period, right? So here we also have the gradient too. So this is kind of z. Z. So this is basically, if you apply the B1 constant over tau, ZZ constant over tau, mathematically what's happening is this in different locations. So you're going to have a slice thickness as this, which is what? Governed by the pulse duration and gradient amplitude. So for example, if you want to have like 1 centimeter side thickness, you know all these values, and then you have to choose either long RF pulse duration or higher gradient amplitude or vice versa. So depending on how you use it, you're going to achieve different side thickness. Okay? Any questions? Okay. Okay, so this is kind of the summary for the small tip approximation. Again, we are somewhat assuming the resonant frequency is same as carrier frequency, so we're not really looking at the off resonance. If you don't assume the off resonance, then the Black equation is there's amplitude here. Sorry, Black equation will be expressed as a matrix form, and then by assuming mz, which is longitudinal magnetization, is almost same as m naught. By using a small tip angle approximation, basically your magnetization in the transverse plane will be expressed as a Fourier transform of B1, which is centered about their center of the RF pulse. Okay? So excitation profile or the slice profile is just a Fourier transform of the pulse. So this kind of opens up a lot of opportunity for research, because previously, kind of if you have ideal situation, like you want to have really good rectangular pulse duration or rectangular shape, but then you don't know how to design it. Now you have a tool for that, so you can actually design those RF pulses. Again, this is the Black equation. By solving the Black equation, by approximating something, and Black equations are nonlinear, so the behavior is very nonlinear. Meaning, maybe like it works fine until like 89 degree, but then suddenly it's not going to work for 90 or 91, right? It's not like gradually bad or something. It suddenly like breaks off and then it doesn't work. Surprisingly, as I said, it works pretty good up to 90 degree, but then more than 90 degree, it's a problem. So you can't really use small tip approximation. So this is kind of like very contradictory. Like you're assuming m naught is equals to m0, theta is almost really tiny. Cosine theta is almost 1, but surprisingly, it works up to 90 degree really well. So this is an example, kind of like the original paper was 1989 from John Pauly. So this is when you have a 30 degree and when you have 90 degree. It looks pretty similar, kind of in terms of kind of expectation, and it works really well until 90 degree, which is not a small tip angle. So it's fairly popular, particularly if you want to have like a very quick idea on what will be the slice profile for a regular flip angle, like 30 degree, 50 degree, 60 degree. It works really well. But if you want to really understand like inversion pulses, like 180 degree, or saturation pulses, which is kind of 90 degrees, it may not work as well. But for regular excitation kind of slice profile, it works really well. Another one that I will like simply touch it is about the truncation artifacts. As I said, what's the Fourier transform of the rect? It's a sinc, right? So if you really want to have a rect as a slice profile, what do you want to have? Sinc as an infinite length, right? But you can't really have infinite pulse durations. You have to have a very short pulse duration. Particularly question, if the RF pulse is long, what's the problem? Like, for example, if the RF duration is like 30 milliseconds, why it's a problem? Why no one uses 30 millisecond RF pulse duration?
What if it's 3 seconds long?
Yeah, what if it's a 3 seconds? Because as I said, it's longer, the pulse duration is long, then you have more control on the kind of slice profile. The slice profile will be really looking good. So what's the big deal? Like, why 3 seconds? Relaxation. Which relaxation? Can you be specific? There's a T1 and T2 relaxation. What's that? So T1 relaxation. Could be. Why?
Why does it just depend on the pulse sequence? Like if it's an inverted pulse.
So let me just kind of be more specific. Here we're talking about the excitation. So excitation means you exciting and recording signal, whether it's a gradient echo or spin echo. Does T1 relaxation matter? What's that? Right, so scan time definitely longer, right? Which is not good. Meaning if your repetition time is like 3 seconds, by just having that RF pulse, which will make the scan time much longer, right? That's one thing. What else? Right, so relaxation, I think we have to be more specific, kind of T1 and T2 relaxation, because those are very different. Why T2? Why T2 matters and T1 doesn't matter? Maybe
Measuring transverse magnetization.
Right. So once you excite the spin, everything matters is actually transverse relaxation, T2 relaxation. T1 will be matter for next repetition. So T1 will be affected. It's going to be affected a little bit because having a long RF pulse, it's going to have long recovery time. So the next TR, it's going to be affected. But at least looking at the excitation and signal recording, it's T2, right? If it's really long, echo time will be long, and the T2 relaxation will kill all the signal. So meaning, even though you're having a very sharp slice profile, but you're not going to have any signal left. So your signal will be really drop off by the T2 relaxation. So it's not going to be practical. So short pulse duration is critical to make scan time faster and to make echo time shorter so that it boosts up the SNR, boosts up some of the T2 contrast better. Right? Or T2 star, avoid T2 star problem. But then the issue is actually when you try to cut the pulse duration short, what happens? Your slice profile will have truncation artifacts. Because think about it, if you have a very short sync pulse, in the rect side, there will be a lot of oscillation. So that's so-called this kind of out of size profile issue or the truncation artifacts. So meaning, if you only have a certain duration on the sync pulse, then you're going to have a lot of oscillations and out of size oscillations too. So within this slice, there will be some fluctuation, and outside slice, there is contribution. So it's kind of problematic. Always people want to have reduce this or reduce that. And depending on whether this is okay or that is okay, you can make RF pulse differently. So there are actually different ways to design the RF pulses depending on whether this is important or that is important. Or make kind of compromise between two or something. easy way to get around it is actually so-called a windowing function. So like this is a Gaussian window or Gaussian shape. Oh, okay. So kind of like you can actually apply the kind of Hamming window, or the Gaussian pulse to get rid of all this truncation out there. So it is possible to do that. But then the issue is actually always whenever you try to get rid of this tends to be blurred. So your excitation tends to be a little bit kind of blur, meaning even though you're saying like you have a 1 centimeter side thickness, eventually there are some signals coming from outside 1 centimeter, which can be also a problem too. And sometimes it's very, very hard to detect because normally it's projection. Whether this is coming from outside 1 centimeter or inside 1 centimeter, it's almost impossible to tell once it's projected. Your signal is always projected for the slice selection, so this is kind of hard to tell unless there's a huge problem outside the field of view or outside the slice. Okay, so that's pretty much it for today. So next time I'll be actually covering a little bit on block simulation again, using MATLAB and kind of comparing with the small tip approximation. So using a numerical tool, you can actually do the simulation using block equation directly, which may take some time, but this is the exact solution. You also can do a similar job using an analytical solution using small tip approximation, and see whether those two are similar or whether they are different. And also, Wednesday, I'll be talking about the frequency and phase encoding and 2D and 3D or multi-dimensional imaging stuff. So that's it. So thank you.
So then, as I